好，我们开始。喂，可以听到吗？后面可以听到吗？好，我们开始上课啊。我们这个课的名字叫 Quantum Field Theory 量子场论。上课之前我们先介绍一下课程有关的情况。我们这个课是研究生和本科生一起上，大概人数的比例是1:1。如果我估计没错的话，是本科生请举手。差不多1:1是吧？然后到目前为止，我们这个课选课的人数还是很多的，就是接近100人。但是有可能这个研究生里面有一部分是可能之前已经修过的，可能是讲转学分还是怎么着，我也具体不是很清楚。OK， 还有一个就是我们这课，由于看到有一位这个外籍的学生这个选课，我们可能是主体部分是用英语讲，有没有问题？有问题的举手。大家都没问题是吧 ？OK， 好的。那我现在把我自己的这个邮箱地址有问题直接发邮件给你。然后呢，我们这个课还有一个比较重要的专业课，我们把这个每周我们留一个 office hour， 星期五morning。其实大家有什么问题，无论是课程有关的问题，还是物理问题，都可以去找我。然后我们这个课有2个助教同学，2个助教，你们上来这个把自己的联系方式留一下，大家有什么问题也可以直接找他们，如果你找我不方便了。好的，然后就是我们这个课的教材。我们推荐2本教材。第一个呢，我知道了。第2个马修说。那除此以外呢，我们刚才是 common 的 reading books。 Volume 1，看还有一些其他的等等这些教材，那么大家感兴趣的话，也可以自己去挖掘一些适合你们自己的教材去阅读。然后我们这个最后成绩。我们初步的这个有没有定死？我们看看到学习结束的时候，大家学习的情况。初步是一定是40%的作业。然后我们不出意外，应该有一次期中考试。然后我们还有一次期末考试。大家对课程有没有什么问题？本科跟这个研究生两个课在一起上。我6年前讲这个课也是用英文讲的，你是觉得英文有问题？
我是觉得如果是语言写的中文的话，那可能那个外国同学他选这门课的时候发音也不好，这样
不是，我先问你一个问题，英文你有没有问题？
也有点问题，看随机。
那我们试一次看。还有其他问题没有？
老师，这个期中考试时间？
期中考试什么？时间还没定，这没 fix 的。OK。还有没有别的问题？你说我们两个考虑。这样子，中文还是英文？有问题吗？我们经常用英文出的。你觉得有问题，我们可以看看人家专业的需求，用中文。这有一个，当然不是仅仅为了一个外国学生啊，最主要的实际上是为了，因为这个课程是个 advanced 的课程，可能是我们物理系最高级的课程一个课程。那这门高级的物理的课程，我们如果像12年级的话，用这个中文讲，你可能到时候出去跟别人没法交流，你不知道在别人在说什么。我刚才不是 check 过了吗？你觉得也有问题？我们再投一次。我们现场投不就挺快了吗？好，那我们再 check 一次，好吧？觉得上课英文上课有问题的举手。1个、2个，不要害羞啊！3个、4个、5个、6个。Okay, that's the problem. 这我没有预料到，我没有这个。好，那我们还是按刚才的，因为只有不到10个同学举手，那么我们还是上一次大家看一看好不好？你觉得怎么样？你们举手的同学觉得怎么样？可以吗？好，还有没有别的问题？除了上课语言，还有没有别的问题？没有，我们就开始上课。 the first, this course is called quantum field theory. So it will be important question. Well, the first question you should answer is why quantum field theory? Even before you understand what it is, you should try to realize why we should do this. Why people invented quantum field theory. This is a very important question to motivate young generation to study or even develop. So why quantum field theory? Do you have any idea? Yes.
To reconcile one mechanical.
Good. Okay, any other opinion? That's indeed one of the most important reasons. Quantum field theory is a result of quantum mechanics plus special relativity. Actually, are you okay with speaking Chinese? No? No? At all? Okay. Special relativity. So I put this is a result, okay? Means this is not a choice, it's not an option. It's a consequence. It's a consequence means you have no choice. So this means then we should understand why, right? Why this is an essential consequence of when you put together quantum mechanics and special relativity. To understand this point, we realize that it doesn't make sense to essentially, okay, before I explain the details, essentially the point is it's not okay. There's a huge trouble, there's a problem if you maintain all the concepts in quantum mechanics when combined with special relativity. So hopefully you know something about quantum mechanics, so then it's easy to discuss. So in particular, it doesn't make sense to, for example, maintain the wave function interpretation. Or say naively, if you put together quantum mechanics and special relativity, you might try to suggest something called relativistic quantum mechanics. Okay? So what do you have in mind if someone try to ask you to write down something called the relativistic quantum mechanics? What is your first mind to do that? Any idea? Any idea? The naive thing is to try to say, write down the equation for relativistic quantum mechanics would be you replace the most important equation in quantum mechanics, the trillion equation. Is this equation familiar to you? Yes? Okay, hopefully everybody, yes. To what? someone asks you to just improve it to be relativistic, what do you do? Make the operators to be relativistic, right? Right? Then you will say, okay, usually let me try to write down another equation. Perhaps I'm done. Okay. What is this equation? Yeah, this is the so-called Klein-Golden equation. Now, even more, you want to maintain all the concept. Concept means how to interpret this kind of equation, all the objects. If you want to maintain the concept, even for this improved equation, you have trouble. So what is the meaning of this slide? Quantum mechanics. We know psi and the psi bar or psi norm square is something. What is that? The meaning, basic meaning of that is probability density. Okay? Probability density. Now, naively, you will again try to interpret this psi. Okay? You put psi norm square or psi times psi bar, meaning that psi should be complex value. Okay? You naively will try to interpret that again as a probability density. Then you realize it doesn't make sense. It doesn't make sense. Because as a choice, as a candidate for probability density, you have to satisfy several crucial properties, okay, like long negativity. So this is the trouble, or even more that there should be, the probability should be conserved. Okay? The entire probability should be time independent. Okay? Then you realize that if you naively try to interpret the psi here as psi star here as the probability density, you have trouble because you couldn't find any candidate basically. Not only psi star, you can just try to do experiment. You can find that there's no choice, no candidate for to satisfy the property of this probability density. Okay, first one is non-negativity. The second should be conserved. Okay. So if this is the first time you hear about this story, then just I suggest you after class try to do it yourself and do the analysis and convincing yourself this is the result. So this means what? Technically, this just means interpret this equation as a relativistic quantum mechanics equation. Basically, it doesn't work. Okay, it doesn't work. Or something called relativistic quantum mechanics actually doesn't exist. No such kind of thing. But actually, in old days, people indeed try very seriously to go this approach, but it doesn't work. So we believe relativistic quantum mechanics does not exist. Now this reason I put here looks a little bit technical. Okay, looks a bit technical. Actually, there's a more fundamental reason for argument, you can convince yourself. Indeed, it doesn't exist. So at fundamental level, it's actually easy to understand why relativistic quantum mechanics does not exist. We have actually a very good reason why. Since fundamentally particles can be formed and also this means what? It means that if you try to boost a particle which carries a huge velocity, the kinematic energy will be compatible with the rest mass. Okay? Or you learned already special relativity. Okay? So you know what I mean. In special relativity, we have the famous equation, right? What's that equation? E equals to mc, right? And we also know the mass and energy can converge to each other. Okay? So we try to boost the particle to a high velocity. When the kinetic energy is compatible, even greater, okay, than the rest mass, then physically it can very easy to decay into two more particles. Okay? So that's why we say that in special relativity for relativistic particle, the particle number is ill-defined. Because eventually the particle can be formed most of the time. The particle number is not a well-defined quantity, which essentially means the any point of non-relativistic quantum mechanics doesn't work. Okay? If the whole point of non-relativistic quantum mechanics is put up on the particle number is fixed. If you remember quantum mechanics a little bit, in the usual quantum mechanics, if I have one particle, I put the wave function for a single particle. If I have two or even more, I put a uniform wave function for all of them. But we never talk about the particle disappear and some particle generate. Don't touch down the process. But essentially, in relativistic limit, there's no way to avoid that process. This makes we have no choice. So we have no choice. We are meant to encode that field. Okay? And you will soon see white fields, right? Not other concepts, right? White fields. Fields essentially means that fields can characterize the process. Coupled with the usual non-relativistic quantum mechanics. That's a property of the field. The field is essentially the infinite number of degrees of freedom. Okay. So this is the first reason why we need Let me try to put another additional reason why. The additional reason will be very, very close to real world, okay? Very realistic. Because in our real world, everywhere there is a field, okay? You learn very well, for example, light, electron, at least the Maxwell equation in the middle in electromagnetic force. That's a very typical real-world field, right? We know that's field. We know light is field. Right? But before this course, you might only understand EM is a field in a sense in the classical level. So we know it's a classical field. Okay? The defined property is described by Maxwell's equation. On the other hand, we also know our world is truly quantum. Are you okay with that? Yes? Okay. So what? So we have to quantize. Have to do quantization. For sure, if you combine these two, you will quantize this one. Seems also you don't have much choice. Okay. This through. Let me put one more reason. It's a little bit technical and also important. Up to now, including this one, this reason, and this reason, you might complain. Okay, why do you always care only about the fundamental level? Our real world is very rich. We don't see scale. We know microscopic scale, also macroscopic. Some people even argue that there's no meaning to talk about which one is more fundamental. Okay, but anyway, we don't want to discuss that philosophy here. But as one additional reason, if, for instance, if major you are trying to do research in concerns matter field, concerns matter physics, that's concerns matter physics. Even that, even you forget about the fundamental work. You talk about some real lab system, an actual system, the system with a chain of atoms, electrons, then quantum field theory is also cannot be avoided. Because quantum field theory is essentially the continued limit of many systems. The discrete system, or lattice. Okay? For example, I can give you a lattice system. Do you have any picture? Have in mind if I say something like lattice? Lattice is very simple, right? Just hand you some atoms. Just lay into some square lattice or some more complicated lattice. Then one thing you can do is you try to take the continuum limit, meaning that I can take the elementary distance between each side, each atom, go to 0. Okay. I can take something called a continuum limit. Then the claim is you will get quantum field theory. Okay. You get quantum field theory. Actually, this is a very, very good picture to really understand or to establish your intuition about quantum field theory. When I myself learning quantum field theory, I always ask myself, well, what is it? You give me a 100 formula, but that doesn't mean I understand it or it's clear what it is. Okay. So you at least you should keep one picture in your mind. What is one picture? Now the best picture I would suggest is some kind of picture. It's a lattice picture. Now you can also complain that okay, this is just words, right? Okay, it's just words. I mean, it's not very concrete. Right? It's just words. It can be made very concrete. For example, if you consider some atom or even just any point mass is attached or glued with some spring, then there's another atom. There's another spring, there's another atom, there's another spring. Okay? So it's a very simple system, right? Making this chain, even if long, you can even increase dimensions, make it two dimensions, three dimensions. Okay? Then you try to write down very confidently the dynamics of this system. Then you can try to take the complete limit, try to redefine the priming. You can convince yourself, indeed, you can find this one. Okay?
Here, like, it would be when you look at the triangular equation. But you just say it doesn't make sense to maintain it. So it doesn't make sense for this series to exist, right?
No, it doesn't make sense for different question, right? This makes sense, meaning that it's not possible to keep the original concept. Indeed, we will immediately realize that this is the correct equation, but for different interpretation. Okay?
So why?
It's a field. So psi is not a wave function. That's the point. So even in this one, for the continued limit, if you get the similar equation, you should really keep in mind that that's the field. It's not a wave function. Find another function. That's not the point. Any other question?
How do you integrate the point on the lattice?
Point on the lattice.
Yeah. So there's a field there.
Okay. You want me to write the equation for you? I can do that. Do not risk the losing part. Yeah, I can write the equation for you. Okay, maybe somebody another part. 这个系统就是很简单，就是一个原子弹，我待会儿可以，这边就是一个汤宝。这个 point mass 就是一个 atom， 就是接着一个汤宝。这个公理学是很简单的，是吧？ You can write down the Lagrangian Hamiltonian. Let me do this. So for this chain of a spring with point mass system, then we can try to as Euro make a notion of this smallest distance A, okay? And we can try to take A goes to 0 limit in the end after getting a very concrete boundary on the point. The point is we can try to now x is of course the coordinate, okay? And use x to lead the position. So which object I'm talking about, which position. So x is the point mass position. I use n to label which one. So I can try to describe the deviation of the original position as some new variables. Use some variable. Find and Okay. So what was the meaning of that? 0? 0 means you can think it's at t equals to 0. Okay. At t equals to 0, located at on the x-axis 0. Now I'm trying to characterize what is the dynamics of the eta n for this system. Is that very fun? Is a classical mechanical question. Okay. Maybe to solve it. 1 or 2 years. For example, I can write down the Lorentz, which is the kinetic energy subtract the potential energy T13. This will be like, of course, this should be a sum of n. There are many objects. You should be able to get some terms like this. Or some other terms. Okay? With some coefficient, in particular the localization doesn't really matter much. You can always redefine if you want. Some content. For example, you could write down the dynamics of this system. So Lagrange for this chain of mass attached to this spring as follows. Okay? Now this becomes concrete. Okay? It becomes a homework exercise. Now given this one, we can do, say, take the limit, a equals to 0, a equals to 0. Okay? So what happens for a equals to 0? It becomes continuous, right? The sum, in particular, the sum will become a what? Integral. Okay? The sum will become the integral. Now the sum will go to become some integral. Okay? Integral of what? So it's integral dx. Okay? You can calculate it very concretely. So after this continued limit, we essentially get free fields up to some redefinition of this coefficient. Okay? Okay? So that's everything is not this no approximation or everything is very concrete. Okay? So you get free fields. So this is the 3 reasons. Of course, you can find more reasons. Okay, depends on which viewpoint they are standing in. There are many reasons actually to argue that quantum field theory cannot be avoided. And, for example, we know in fundamental level. We have 4 different forces. Okay? 4 different forces. What are the 4 different forces? Anyone say what are the 4 different forces? Let me test my English speech. You can understand that my English. I will ask someone. Did you try? Anyone can try? Yes.
Strong weak gravitational.
That's correct. So, at fundamental level, we only have 3 fundamental forces. Okay. But the point is, 3 of these 4. We know 3 of them. Okay. Have already been perfectly described by quantum field theory. So if you want to try to understand anything in fundamental level, here quantum field theory is not avoided, cannot be avoided. The only remaining one is gravity. Okay? We don't know how to incorporate gravity in the framework of quantum field theory. But of course, this shouldn't be the reason we should forget quantum field theory, right? And actually, oppositely, this becomes a challenge for you guys try to how to develop the quantum field theory. And, personally, I would believe the next development, next revolution of quantum field theory can possibly solve this problem. So, any question about the motivation for why we need a quantum field theory? Yes. Okay, that's a very good question. Good. That's a good question. Yes, at some level, we don't need to think about that process, as you were already learning in your second year bachelor activity. Your lecturer, your teachers never talking about this burning particle, something like that. But the point is, we're talking about now particle, quantum particle. Which means we're really standing common work. So we should go beyond that after in that sense, you do not avoid the quantum mechanics. And you combine it. So there's no simple way to stay in that work. I can interpret all this. Other questions? OK， 我还有一个问题，就是关于我们这个什么时候下课，要再来测试一下。我们有3节课，我们是 follow 铃声下课，还是中间休息一次比较长的？我们中间休息一次，20分钟，就 break 一次，因为我们这可能有很多东西。要写一些长公式啊什么。Is it okay? It's okay if you are not okay. Okay? Good. Good. So, these are the motivations. So eventually, what is quantum field theory? We are talking about we need it, but what is it? I feel that I may go very slowly, so you need to speak up a little bit. So after all, what is quantum field theory? This will be also very important question. So very roughly, okay, I would like to just make a very rough intuition for you. If you never hear about this word or concept before. Okay, so what is quantum field theory? Of course, quantum field theory we already realized it should be very complicated, right? With infinite degrees of freedom, you look at that example. It's like infinite number of point mass. Okay, each one will just fall into a particular dynamics. Right? It's very complicated, that's for sure. So after all, we can get some intuition of QFT, which is essentially just very roughly. It just means the classical field, as I suppose you are familiar with, now becomes operators. In Hilbert space. Now I use this sentence to try to offer you some understanding of what is quantum field theory. Of course, I assume you know what is operator and what is Hilbert space. Okay? Is there anyone who don't know what is the operator and what is Hilbert space? Raise up your hand. I can explain, okay? I'm going to fill out the concrete concept. Okay, so everybody knows what is the operator, what is the Hilbert space, okay? So very roughly, it just means classical period now becomes the operators, or in another word, these phi and t now to be understood as operator valued functions of space-time. Okay? Operator value the functions of space-time. So this kind of interpretation or description is actually very important for you to understand the quantum field theory. Almost every problem or difficult things in quantum field theory. The point is, whenever you have some really problem to try to find with something in QFT, you should always go back to quantum mechanics. Okay? You should always go back to quantum mechanics. Because it's essentially a quantum mechanics with a lot of degrees of freedom. Okay? That's the lesson. So in quantum mechanics, we know typically we're talking about a variable, okay, or degrees of freedom, which is described by what? The easiest one is what? For instance, position operator, okay? You should be familiar with. Now, in order to emphasize this linear operator, I put a small hat here. This is the x hat. In quantum mechanics, you are always dealing with the x hat. Now, I just claimed in quantum field theory, of course, the whole point of this course, the entire course, is trying to explain that sentence, okay? We're trying to make it very concretely. So here I'm trying to compare with quantum mechanics in the quantum field theory. So the analog of this x hat will be now phi. Okay? We want to emphasize if indeed an operator, I put a hat here. Okay? So you should try to understand the analog of the previous x hat now becomes phi hat. Okay? Of course, in the same time, this would mean that now the interpretation of the new framework, theoretical framework, the x is no more an operator. Okay? That's very important. Okay? Otherwise, you will always be confused. Now, it's not an operator. It's what? It's just some labeling. Okay? Some label, some index. Right? That could be very clear from this chain of point mark picture, right? Look at this picture. X essentially is a continuous limit, just to tell you which point mark they're putting. Just label with degree. Now the true operator turn to phi itself. Okay? Phi. Phi now becomes the operator. Okay. Now in quantum mechanics, we also talk about the state in a sense. Okay? Because we have operator, we also have state, right? That's the fundamental language in quantum mechanics. For example, I can talk about the eigenstate of position operator. Okay? This state. Now, you can also make an analogy of this one. Analog things for this state Of course, correspondingly, this state is corresponding to this operator. I can also make a state notion, QFT, which will be what kind of state? Okay. Clear? This state is the eigenstate of this operator. You see? Now even more, right? We can also talk about wave function. Wave function. So some real world particle or many particles or something else. In general, the wave function is not as simple eigenstate. Right? It will be complicated thing. It has a non-trivial profile. It's like it has a non-trivial profile. For instance, in order to resolve this wave function, you take the inner product of overlap between some state psi with the x. Okay? You get phi x, right? That's your first course in quantum mechanics. So you get something like a psi x. Okay? Psi x. This is your wave function. Now in QFT, you actually also have that object, the wave function. We call it wave function. So what is that? So in quantum field theory, just try to make the analogy for quantum mechanics. Because I just told you, QFT is nothing but quantum mechanics with a very, very huge number of degrees of freedom. So this is wave function, okay? Wave function of what? So this in QFT, you see, always wave function should be expressed as a function with the variable. The variable is the eigenvalue of this operator. You see? Let's make this logic very clear. Right? This is x. Okay. So what is x is a number. What is that number? Where it comes from? Number comes from you act this one on this state. Okay. So this should be expressed as a function of the eigenvalue. Okay. So now the eigenvalue in here is just phi x. So if you want to seek for wave function in quantum field theory, you should come up with a wave function, a function law of some fields. Of course, this is this looks a little bit complicated, right? But we should be making it clear. There are some corresponding objects in quantum field theory. So, as a summarize, quantum field theory is a framework to incorporate an infinite number of quantum degrees of freedom, arranged in space-time. Okay? Degrees of freedom are arranged in space-time. Or in other words, space-time coordinates will be treated as an index to label the degrees of freedom. Clear? With the interactions constrained by some principles like locality, symmetry, unitarity, causality, and it is the universal language to write the laws of the nature. If you would, if you ask me to put a definition using words for quantum field theory, that would be the definition. Quantum mechanics is clear. It's just good question. Okay, you should ask that kind of question. Yeah, it's a little bit complicated. You can imagine. Okay. By imagine I mean right. There are a lot of different configurations for fields. Okay, which is essentially the geometric meaning of phi x. Okay? But the point is, in the operator or state language, all those, say, some classic different profiles of this function, phi x, should be viewed as the eigenvalue when you activate the operator on the corresponding state. Okay? Does that answer your question? It's just a profile of a field. So for instance, I consider the field carried a shape as a Gaussian distribution shape. Okay? The eigenvalue is just the field configuration. Any other questions? Yeah. Phi X is an abstract new physical quantity. Indeed, that's what it means. I didn't read the word. What just said? I didn't hear you. Meeting what?
You just physical quantity just by
for sure, it's not that's your simple objects. You only with it's not like a very things like that. It sounds like a distribution. You know, in your course of imagine, you can write down V for I, for V, right? And you add V. Okay? It's no more than that. Yeah, it's the same thing. But the point is, there are a lot of different profiles. Very complicated. Think about this chain of the point mass, okay? Think about this one. It can be different dependence of this x, right? In fact, there are many different configurations. But it's okay. This system is about a infinite degrees of freedom. We incorporate all these different configurations. It's a really complicated space. It's okay. There's different framework to describe the same system. It's like, in usually you can use X or something in this way to momentum space, but all just equivalent. Think about the different profiles. Okay. So define X in one way. Any other questions? Yeah, what's the question? Let's go through that. Yeah, that's the key difference. Again, let's go back to here. Yeah. This plus I is never corresponding to this phi, okay? This plus I is analog to this capital plus I, okay? In quantum field theory, even sometimes you also see some functions, some shapes, but that shape doesn't mean anything, nothing to do with the wave function. The correct interpretation of this phi would be some elementary objects, okay? Or degrees of freedom if you want, okay? The wave function for that degrees of freedom is really, you have to go up level, one level more. You have to go to a function of these different configurations. This is already a function space, a space of functions, okay? Is that clear? For each function in the space, I give some probability, okay? This is called function norm, okay? Is that okay? Good. So I just make a sentence to try to give a principle definition for quantum field theory. Let me write it down. Here. So there is a definition of QFT is a framework to incorporate infinite number of quantum degrees of freedom arranged in space-time with interactions constrained by principles like locality, symmetry, unitarity, and causality as well. Right? This is a possible definition. And in this sense, as I just explained, this is a universal language, or is the language. Okay? We don't have much choice. Our knowledge or our understanding of the nature lead us to this quantum physics. And it is the language to write the world situation. So this essentially means no matter which research field you are working on, there is a good reason to you, even for experimentalists, there is a good reason for you to get a bit of knowledge about quantum field theory, see quantum field theory 1. Of course, we also have some something called quantum field theory 2 or even 3. But at least the quantum field theory 1 is quite universal, and I think everybody should know. So this is the introduction part of this course. Do you have any questions? I don't want to rush into anywhere. Okay, good. Hopefully we're in the same page, so that's good. So, so as I already mentioned, quantum field theory, another very formula definition will be the Qm plus spectral relativity. Okay, so let me start by review the spectral relativity part. To make sense in a concrete way. So special relativity the most important thing conceptually in the symmetry in special relativity, or the symmetry of our space-time, is the Lorentz group. Lorentz group is the group language to describe the symmetry of Minkowski space. Okay? So everybody knows what is Lorentz group? To anyone who doesn't know what is Lorentz group, raise your hand. Okay, good. Thank you for your audience. Any more? Okay. So there's a good reason. We don't want to lose anybody. Okay. There's a good reason to review what is Lorentz group. So what is Lorentz group? So for those of you claim that you already know what is Lorentz group, now there's a question. How many independent parameters to describe Lorentz group? How many? Correct, 6. Okay. So the way to understand what is Lorentz group is just to try to again make an analogy. So what is Lorentz group? Lorentz group is nothing but a rotation. Okay. Rotation in what sense? Rotation is not the simple rotation of our Euclidean space. Okay. It's a rotation in the Minkowski space. Whenever we talk about the rotations, you have to be specified which is invariant. Okay, because rotation is a transformation. Okay, make it clear what is the invariant quantity. When you do rotation, then everything becomes very simple. Okay. Okay. So what is the rotation? Even you doesn't know Lorentz group, that's okay. Okay. I'm sure you will know after 10 minutes. Okay. So what is rotation? The simplest rotation will be a 2D rotation. Okay. The 2D rotation meaning the rotation in the plane. Okay. I have a plane. I want to perform a rotation. Okay. Rotation of what? Rotating what? Rotate what? Rotate my points. The point is described by the coordinates in x and y. Now I want to rotate this one. Okay. Rotate. We can rotate from here by some angle. Okay. Theta angle. And this pointer has a new position. This is what I mean by rotation. Okay. It's actually everybody have the same common understanding of the simplest one, right? So under this 2D rotation, you can easily write down a matrix formulation for the coordinates. Okay.
I'm sorry.
Yes.
Since you label the axis and label here, would you really rotate?
No, I'm not talking about the QFT. Now I'm just talking about the middle school geometry. No, I'm not talking about the QFT. I'm not just trying to review the Lorentz group. Before reviewing the Lorentz group, I'm trying to review the rotation Euclidean space, two-dimensional Euclidean space. I just rotate the points. Okay, there's no physics here. Okay, this is enough. So under the 2D rotation in the Euclidean plane, which is x and y, everybody knows, you should know, under this rotation, I will get a new position. See, x will become x times cosine theta plus y times sine theta. The y will go to also a new position, minus x times theta plus y cosine theta. Okay? If I rotate in the clock direction, or you can also do anti-clock. Just flip the sign of the angle, right? Now a better way to package this transformation will be using something fun, right? It's using something called vectors. Okay. So you can package the same thing. Okay? I did for this step. I just do rewrite. I don't do anything more. The xy will become. I also assume you all know linear algebra. Any question? No. Sin theta minus tan theta cosine theta times the previous x and y, right? So this is my transformation in the 2D plane rotation, on the 2D plane rotation. You see? You can package it this way, right? It's not unique. You can do it in other way or even many ways. Okay. It's okay, but the point is the same thing. Okay? The same rotation. Doesn't matter how you represent this one. Okay. You can represent or package the same thing in another way. For instance, you can package it in this way. You can write xy. In this manner, xy will go to x, y, and the matrix cosine theta minus sin theta, sin theta, cosine theta. It's completely equivalent, right? As you can see, you can realize. Now we want to do something a little bit about the graph. Okay, hopefully it's okay. Again, I just rewrite the same thing in another language. Another language for the index notation. I can just write this one in terms of some index notation. For instance, I can write an xi essentially means the column vector. Okay. Xi, in this case, I rotate it, then it becomes, if I follow the matrix product order, okay? I strictly follow the matrix product order, and this becomes I, J, xj. And I assume the repeated index will start with J. Okay? Is that okay for you? It's the same thing, right? I just write the same thing in some funny way. Or if you want, I can write we call this is column, another is row. Okay? This is column, another is row. Or another one, I can uplift the index. I use xi. This is the row vector. Then it rotates to become the row vector times a matrix. Right? This matrix, this matrix, I call it R transpose. Okay, transpose. R transpose. Then this will be J, this will be I. Okay? Again, the repeated index is fine. Is that okay? Yeah, this is a super easy example, but I want to make the notation very clear. Just to try to convince you. There's always an elegant way to arrange the index or arrange some notation or some transformation. Okay? It might not be unique, that's the point. But you shouldn't worry about it. There are some fundamental difficulties. There's no such difficulty. You really do it in an elegant way. So, you can also check. I make this rotation explicitly in terms of 2 by 2 matrix. Everybody understood. Now, formally, you can also check. In this case, the R transpose times R. Both of them are matrix 2 by 2, right? R transpose times R equals to what? You quickly figure it out. It's identity, right? It's also a matrix, but it's an identity 2 by 2 identity. Is it clear? So, if someone hands you a matrix, it does satisfy this property. In mathematics, we call this is the orthogonal. This is matrix. This is an orthogonal problem. We call this an orthogonal matrix. One can also check, in this case, the determinant of both R or R transpose is equal to 1. If someone hands you a matrix to satisfy this property, we call what? We call something special. So combined with these two, in group theory, we call such a matrix is a representation of some group called S. S means special. Okay? Now it should be also orthogonal. So I put an O here. Okay, what is the dimension of this space? It's 2. So in group theory, such group is called SO2. Okay? Clear? So 2D rotation group, in mass point of view, is the SO2 group. The SO2 group. Simple, super simple, right? Now you can very easily to generalize the n dimension. You should be able to figure out by yourself what is the representation for SON. So n dimension can also do the rotation, the n by n matrix. Just put these two constraints and work it out. But we also mentioned, okay, this is just okay then. Yeah, I first show an example. Then I try to just extract the property, who the features of some kind of transformation matrix. Okay. Then try to connect it with the math language or group theory language, which is the SO2 group, talking about the 2D rotation group. As mentioned earlier, another way to define the same rotation group is just to try to look at which quantity is preserved. So in this case, which quantity is preserved? I erased this picture, but hopefully it's okay. So which quantity is preserved? Which quantity is preserved? The length of this vector. The vector is the vector corresponding to the point, right? For any point with a unique vector, go from the origin to that point. Okay, we can make a one-to-one correspondence. Okay, then we have a notion of vector. Then you can measure, we can calculate the length or the length of this vector. Okay, and you easily find that quantity is preserved. So in my abstract index notation, now I'm trying to use this new notation. Because after I invented this new one, why don't you just use it, right? It's convenient. So you can easily check this object is preserved. Preserved means it doesn't matter you rotate by which amount of angle. It's okay. It's the same. You get the same value for the new vector. Okay? The length is preserved. You can easily check it. Can you see this is preserved? Yes? How? How to show this is preserved? We can show it, right? Again, let's check after the rotation. What happens? This will become xj. As said there, rt. Okay, j, I. Then for this one, it will become the r. Was I, k, xk. Okay. You have to be a little bit careful when you have many or multiple index. Okay. For instance, you might just sloop, little bit sloopy, just put this as an I. It's okay, but you have to make it clear, at least for yourself, which one is summed repeatedly with which one. Okay, which one is summed together with which one. Don't confuse yourself. For instance, in this case, from left to right, as you can see, we have only an I here. Okay, you should have a corresponding I in the right hand side. Now, it essentially means the J index is repeating. Right? Repeated index also means some index you create, okay, in the right hand side. For that kind of index, you have to avoid trying to get the same notation with the previous repeated index. Okay, just choose another one. In this case, I put a K here. Okay? Then things will be clear. Okay? Is that okay? Yeah, I understand this might be too elementary for some of you, but we have a huge number of students. It's better to make sure we are on the same page. Okay. Seems clear. Now, to this step, okay, because of the property of the rotation matrix R, this essentially equals to what? This equals to xi or xj. This equals to xj delta kj xk. There's a delta, okay? There's a delta kj here. This essentially equals to xj, which is the same thing as this object. You see? Why is that the same? It's just repeated image. It doesn't matter you label it in I or j, okay? It's the same thing. So we checked this is the norm of this vector is preserved under the rotation. But the point is we should think it in the inverse way, okay? You should think that you can define the rotation matrix by demanding this quantity to be preserved. Okay? Then you work out that transformation, you find that this is nothing but a rotation. You think that this definition is more deep, okay? Even better to understand more complicated things. You should always keep track of which quantity is preserved. Okay. Yeah, maybe let's have a break. And you can continue. It's a good place to break.
你要是半期的时候考得特别差，考到最后，然后你的期末考到成绩，你是有概率他觉得你进步非常给你回。
然后呢，如果但是我
那就这个好的，也不都可考的。我要过10那你们学对呀。我休息几个，但是给我整了。哎呀，这个应该那时候80页书，读到最后还要写一篇论文，我真可以说是而且虽然我线上考也无所谓，我现在考的是上半年期末是知道直接把我的写环节给取消了，然后把它讨论到随便改个2个字，所以结果我改起来就是老师讲小丑了，看来我对反国家就是小丑，反小丑同事。就是这种课吧，
喂。喂。 喂。后面的同学可以往前坐一点，因为可能声音这个麦可能有点问题啊。我上次问过了，这是他们最好的设备。喂，没效果。喂，这个好一点吗？啊？我倒只能这样讲，这个OK。好，我们接着上课。So we just discussed the rotation group in Euclidean space. And importantly, we claimed a better way to define the rotation group is try to figure out which quantity is preserved. Now in Euclidean space, the length of the vector is preserved. Now if I try to make an analogy to do the same thing but now in the four-dimensional space-time, which means that now try to push or extend this definition to encode this time. The first thing we should figure out again, now let's take the simple definition. So in Minkowski space-time, which quantity should be preserved for the Lorentz group or Lorentz transformation? Okay, that's the first question. Okay. Now even before that, we should make the location clear. So now we work in a four-dimensional Minkowski space. Now we choose the space-time coordinate x mu with the upper index is t x y z. Okay. Now if we want to try to define the Lorentz transformation by first figure out which quantity is preserved. Okay. So So this quantity should be the analog of this length of this Euclidean vector, vector in Euclidean space. In other words, it should be the length of some four vector. In this case, everything becomes the four vectors. It has to be record this kind of object as four vectors. So which quantity associated with this vector could be preserved in complex space-time under Lorentz transformation? Do you know? Anyone knows? It should also be Lorentz, right? But in this time, since this space changed, the definition of the Lorentz goes a little different. No more the simple, the Lorentz defined in linear space. Rather, it should be the Lorentz we call the proper length or physical length between two space-time points. So now we have one more time direction. So in fact, in any space, if you want to try to make a general definition of the length of your vector, you should contract with something called a matrix. In this case, again, follow the matrix product order. It seems very clear. We want to measure the length of this vector x mu, we should compute this object. Is it clear? Is it clear? We should contract with the metric. In Euclidean space, this is just a trivial identity. But now, the metric is a little bit non-trivial. It's the metric in complex space-time. In any sense, you want to compute the length of this x, which is the following. So this is what you should be familiar with in your spectral activity course. This is nothing but t squared minus x squared minus y squared minus t. See? This means that I choose the metric in both the minus notation. This is my metric structure. So Lorentz transformation, by definition, should say Lorentz transformation now I will write is some transformation for this four vector x. Okay. Now if I build too many index, I want to actually avoid the index. I want to be a little bit abstract. I want to just take this notation as a matrix. In this case, x is what? It's a column vector. Column vector. Okay? Column vector is ended by one matrix. Right? So a Lorentz transformation will send this four vector to another four vector lambda x. Lambda is also a matrix. I use a dot here. Dot means matrix product. So this kind of Lorentz transformation, as said, by definition, it should preserve the law. Now, to write this law in another way, in that matrix product notation, it should be a x transpose dot g. G is also matrix. The matrix for the matrix. G times x. Okay? This, by definition, is the law of the four vectors. Okay? Sometimes we also denote it in this way. Okay? This means the log, right? If you have vector, this means log. Okay? 1 squared. Now, under the transformation, this arrow always means transform. Okay? Transform from A to B. Okay? From left to right. So under Lorentz transformation, by definition, we will get a new vector, right? Because x will become lambda x. we should replace the x by lambda x. Now the point is the norm will be unchanged. So this will give us the equation x transpose lambda transpose g dot lambda dot x. Okay? This is the norm of the vector after transformation. You see it? You see it? Yes. Now, by definition, the norm shouldn't change. This should be equal to the previous norm, which is x transpose dot g dot x. See? So just follow the definition. I define the lambda. Lambda here is the Lorentz transformation matrix. You see? Lambda represents the Lorentz transformation. Following the definition, I will get this equation. This is the property or the equation is lambda to satisfy. See? Because lambda is my notion for the Lorentz transformation. Now, it's clear, following this kind of definition, you can easily figure out the defined property for Lorentz transformation, because this equation, you just simplify this equation, you get this will be equal to this. See? That clear? Now, by this definition, we get a formula or equation for the lambda, which is very important. Complicated to carry this mind. Here is my note. So that definition will be nothing but lambda transpose g and dot lambda equal to g. Okay? This is g. What is g? That is g. That is my g. This is my g. Okay? This is my g. This is my metric. Clear? So this is the definition of the Lorentz transformation. This is actually the defined property of Lorentz transformation. Now this is very abstract, or you might complain this is too formal, indeed, but it's clean and it's simple. It's a good way to give this definition. Now, in order to understand it in an explicit way, okay, rather than this abstract equation, we should make it clear what this Lorentz transformation does, which job this Lorentz transformation does. Okay. If you think about it for a few seconds, you should immediately realize that this Lorentz transformation, this definition gives you some Lorentz transformation, which is lambda, should also include the rotation among the spatial directions. Is that clear? Why? Because if you only rotate the spatial directions, the x, y, z, okay? Don't touch time, okay? Because this is a 4 vector, right? T, x, y, z. Okay? Is a vector stay in the 4-dimensional space time. Okay? If you only rotate among x, y, z, okay? It for sure it will preserve this G metric, you see? Okay? Right? Because this definition is just coming from, inspired from the Euro-Euclidean rotation group. Okay? And the 3-dimensional space is a subspace of the entire 4-dimensional space-time, you see? So if you rotate only among the 3 spatial directions, it for sure it should be included, or it's an element of this. The entire group of these Lorentz transformations, right? That's one thing you should easily understand. Now, what about time? Okay, including time, we learned from special relativity there are something different compared with only x, y, z. Because time there is minus 3 minus, but this is plus. Okay. For simplicity, let's say forget about y and z. Only consider x. For instance, according to the definition, the quantity I should preserve is t squared minus x squared. Okay? So the Lorentz transformation should do the job to preserve this t squared minus x squared. T squared minus x squared is special relativity called the top limits. Now, which kind of transformation will do this job? That will be the question, right? We just already figured out, classified the only special rotations among special directions should be included in the Lorentz group, right? Now, what's more? Okay? What's more? What's more? That object is the so-called boost. Should learn that in a special relativity course. Boost is essentially the transformation preserved t squared minus x. What is the boost? Boost means there are two different frames, right? Take one of the frame is your reference. See the other frame. That frame can carry a non-trivial velocity compared with this frame. Okay? Boost essentially means that different frames has a relative velocity. That's the boost. So that boost will offer another transformation to preserve t squared minus x squared. Is that clear? Would you feel that this is complicated? Let me try to speak louder. So putting everything together, combine include these special rotations and the boost, there will be totally 6 independent transformations for the Lorentz group or Lorentz transformations, okay, in the entire 4-dimensional Minkowski space. Let's say rotations. This rotation really means the Euclidean rotations. Let's say you can rotate around different axes. Let's say x, y, or z. Okay? So this is the x, you can rotate it this way. This is the y, you can rotate it that way, something like that. Okay. Now express this rotation in terms of 4x4 matrix because your space-time now becomes 4 dimensions. Okay. Vector is 4 dimensions. Your order matrix should be 4x4 matrix. So this will be matrix looks like this. Cosine theta sine theta minus sine cosine theta. This. This is the cosine y. 1 minus sine y. Sine theta y. And here is cosine. And then the last one will be this 1, cosine theta b, sine theta b, minus sine b. Put one here. Okay. This matrix essentially means the block of the entire matrix is essentially again a 2 by 2. Okay? You forgot about the other two directions. This is essentially meaning that it only changes those points or vectors in this YZ plane. Okay, because it is rotating this way. Okay? You see, doesn't change anything else. Okay, this matrix does the same job. It only change the points arranged in XZ plane. Okay? Same thing for this one. They only change the points in this XY plane. Doesn't touch anything else. So all the others are just one. One means trivially acting. Okay? Trivially acting. Now we also mentioned that there should be a boost. I'm not going to derive these boost transformations. You should learn that already from your special relativity. But let me just mention it. The way to get it, or the immediate way to get it, is, let me first write down what it is, and then explain. There will be also a boost. Boost, that's rotation plus boost. Boost, there are also three independent boosts. One is the boost along x direction, y direction, or z direction. Okay. For instance, x directions, the transformation matrix will be represented by cos and the sinh functions rather than cosine and sine. Okay. The follow-up two will be essentially the same, they arranged in different positions in this 4x4 matrix. Okay, this is the sinh. This is the sinh. This is the cos. Here's one more one. Okay. Here's the last one. Here's the cos. Here's the sinh. The last, and in the middle there are two. There's one more sinh, and there's another cos. Okay. So the immediate way to get this transformation matrix is by noting that. So what is this beta, by the way? This beta is essentially the boost parameter. So the cos beta will be equal to 1 over square root of 1 minus v squared. The v is just the relative velocity between two frames. Okay? Familiar to you? Hopefully. Now let me explain briefly how to obtain this matrix. Okay? Now one thing you can immediately check is for a non-relativistic limit, which means this velocity goes very small compared with 1. Okay? We take natural units everywhere, meaning that we take c equals to 1. C is the speed of light. Okay? Now we characterize all other velocities compared with c. So by non-relativistic limit, we mean that v will be very small, meaning smaller than 1. Okay? So in this low speed limit or low velocity limit, okay, you can easily check this transformation just simply becomes Galileo transformation. Okay? Because that's what we learned in middle school. Okay? Galileo transformation. No relativity. Just simply. If you have, we have two frames, okay? And one frame is x, is the relative velocity to v. The other frame at the same position will carry another coordinate, which is x plus vt. Okay? That's the Galileo transformation, which appears laterally from this matrix when you take this limit. And actually you can uniquely determine this transformation matrix by demanding two things. One is the V is very small, you should go to X transform to X plus VT. Just said, this is one demanding property. Another demanding property is you should preserve this norm of these four vectors for proper distance. I require these two conditions. That transformation is uniquely fixed. I'm not going to prove it here. I suggest you to do it yourself. Try to show this is indeed the unique choice. Is that clear? Up to now, any question? Okay, this is the three independent boosts in different directions. That's the three rotation matrix. Okay, so combined together. What do I mean by combine them together? Okay, we're not now teach a group theory. It's not a group theory course. Okay? I'm just trying to show you these are independent Lorentz transformations. Okay, essentially corresponding to the question I asked: how many independent parameters to characterize the two Lorentz group? It's six. See, there are six metrics. Six metrics. Those are this beta or that theta, essentially those parameters to characterize the transformation. Okay. Independent means that any one of them or each of them cannot be derived from the others. Okay. They're just independent. Derived means what? See. Since these are just independent metrics or transformation, you can easily combine two of them. This is still a good transformation, okay? For instance, you can combine a rotation with a boost. It's okay. It just means in your Minkowski space, you first rotate around some axis in your spectral space and then do a boost, just falling off the step. Previous step, doing another boost along some other direction. That's it. So entirely, this of course is a good Lorentz transformation. Mathematically, it would mean that if you take any product, or even the product of not more than 2, 3, or even more, just take a product of many of these metrics, you still have a good Lorentz transformation. That's the point. In principle, I can complete this story. Try to follow the group theory discussion. I can try to find go to more formal level to trying to find the algebra structures of these groups. I will not do it here. Maybe after a few weeks, when it's necessary, we will do it. It's also very simple. So Lorentz group or Lorentz transformation is very simple. Just like this mathematical notion here, using this SO2 to characterize this Lorentz group, we also have a label because Lorentz group is essentially a rotation group in the Minkowski space-time, which we denote as the SO. Because it's also a rotation group in Minkowski space-time, and the Minkowski space-time, we have different signs in example than x or t, right? So when you measure the distance, the t direction, t squared, contribute a plus sign, but x contribute a minus, you see. So for that reason, we distinguish those different directions. This one means one time direction, 3 special directions. We put a comma here. So it's also a rotation group. And you can also actually check the determinant of all these Lorentz group matrices. It also equals to 1 in this case. Okay? So we put an S here. So this is indeed a SO mass language, the SO 1,3 group, Lorentz group. Okay? This is a little bit loopy, the claim I just made, because strictly speaking, the rotations or these 6 metrics or any object that can formed by these 6 metrics, all those elements form a group. It's not the entire Lorentz group. It's only the part connected with the identity. Okay? In group theory language. Okay? If you are a very careful person. Meaning what? Meaning physically, all these transformations I discussed so far is always those transformations can be smoothly transformed or collected by identity. Identity means nothing. I don't transform anything, okay? That's the identity. Then I can follow some parameter, I can do continuously transformation, I can achieve this kind of transformation. Yeah. That's the part we are talking about so far, okay? To figure out the entire Lorentz group, there are some other patches or some other objects, okay? In order to understand the other part or the full structure, we have to introduce 2 more discrete transformations. So strictly speaking, this is not the entire SO1, 3. Sometimes people just make some class here. I don't know what that's helpful or not. It just means is the part connected to the identity. So in order to understand the full structure, we have to introduce the discrete transformations, as you can easily check yourself. If I define some other totally different transformations, those transformations is not characterized by some continuous parameter. Okay? It's just, I just transform, for instance, add a minus sign for each spectral direction. Consider this transformation. You can easily check that fits the definition of this Lorentz transformation. See? You check it? It indeed belongs to this, it satisfies this equation. That means it's the element of the Lorentz group, Lorentz transformation. See? Also, you can also do the add the sign in front of the t, and I'll get minus t without touching anything else. So this transformation called the parity transformation, this transformation called the time reversal. Okay? As you can see, here I only touch this spectral direction, here I touch the time reversal. Now you can check, as I said, these are belong to the Lorentz transformations. The point is, since they are belong to Lorentz transformations, the immediate thing you can imagine is that I can also try to combine these 6 metrics or 6 transformations, as discussed before, combine with P or T. Okay. The point is, after combining with P or T, or multiple times of P and T, you get something. That something might not belong to the previous subset of the entire Lorentz transformation. Is that clear? Okay? That's why I just see this, strictly speaking, this any transformation formed only by these 6 is only a subset of the entire Lorentz transformation. So in order to figure out everything, you have to combine with this discrete transformation. Okay? You can easily imagine that, right? Some subset is connected smoothly, continuously way, but in order to jump into the other subset, you have to do some discontinuous or discrete transformations. That perfectly makes sense. Okay, I think I really need to speed up. I think I know. By now, I finished half of it. Partly because of some questions.
Yeah, so these 2 transformations are minus 1.
Sorry?
The that the part reversal is minus 1.
Yeah, it's minus 1. So which one?
Determinant.
Yeah, that's why. Go beyond this determinant equals to 1. Okay. This transformation go beyond determinant equals to 1. It's minus 1. That's right. So sometimes if people want to classify the full structure of the Lorentz group, they distinguish different patches by just looking at the determinant. So some patch is defined by determinant equals to 1, but other patch belongs to determinant equals to minus 1. Okay, that's correct. Any other questions? No, they are not. Okay, they are not. In general, not. It makes sense, right? That essentially means the order matters. Okay, it's not commute. Means the order matters. That's easily understood. Rotations, I do rotation A and rotation B is different from the first rotation B, then followed up by rotation A in general. Any other questions? That's all good questions. Okay, now I just previously a little bit lazy to write in this formal way, but yeah, it actually can be made very concrete. So now, after we understood this Lorentz transformations, we can do something interesting. We can try to transformations are something acting on some objects, okay? Because whenever you talk about transformations, it's better to specify which object are you transforming, okay? Okay? So to better understand how objects are transformed, we can try to classify the object into different categories, okay? For instance, if something is very simple, just the environment under your transformation or rotations, we call they are scalars. Okay? Scalars are those objects that environ under transformations, under lambda. We simply look at lambda. Okay? Now, we can also classify something into vectors. So vectors essentially means if the object, just like this x mu, okay? Just like this x mu. If the object x mu goes transform in this way, lambda mu nu x nu, then we call such object as vectors. Okay? Very naively, you think just if they carry one index and then transform in an elegant way, we call it vectors. Okay? Elegant way means that because we already know what is lambda, okay? So lambda is a matrix, okay? I put the index following this matrix product order in a serious way. Then this is the transformation formula for the vector. Now, you can go more higher rank things, like the tensors. If I have an object like it carry two index, say T mu nu, if it is under a Lorentz transformation, it transforms this way. Then we call such object as tensors. You can also even go higher rank tensors. We call all those objects are tensors. Okay. Is that clear? So yes.
So the upper index
we make the location here. If the index is the upper, we simply the row, okay? Or in other words, if the index itself represents the column index, that's the same thing, right? The shift as a shift is the row vector. Now if the index is lower, I read the opposite. If the index is lower, it's a column. Yeah, that's right. Then the matrix is actually a column instead of a column. Okay. Any other questions? Now, if you classify the different objects in this way, you can easily check yourself something like an inner product. Something like an inner product, say, I take two arbitrary food vectors forming that categorization. I take two Lorentz vectors, and I consider an inner product. Whenever you put an inner product, you have to contract the index, right? You need two vectors. Okay? Transform one of them and make it contraction. That means you get a finite number. Okay? That's what we mean by inner product. Okay? So in Cauchy space, you do it this way. Take the two arbitrary Lorentz vectors V and W. Okay? You take the inner product, meaning that you calculate this object. You calculate this object. Now you can easily check yourself. Sometimes this notation, some people don't like this too complicated notation. That index is simply like V mu or W mu. They are the same thing. Okay? The same thing. But whatever it is, you should keep in mind that in practice it means the calculation formula is the same like this. Yeah. It's just calculate the inner product of two vectors with respect to the metric. Okay. Using the metric to contract these two objects. And you can easily check yourself. Anything looks like this in the language here, meaning that anything have two repeated index contracted over. Okay? There's no more index. Index contracted over in this sense. Okay? Anything looks like this is a Lorentz invariant. You easily check yourself. Just following the definition, you see. You make a Lorentz transformation for each of these vectors. There, meaning that transform simultaneously for V and W. Okay? You do it, you can try it, right? Transform V and W, essentially meaning that you have a lambda, insert a lambda here. Okay? Lambda transform here and lambda here. Right? Then, following that definition of this Lorentz transformation, so that's a lambda. Lambda transpose times G, times lambda should be G, right? Following that definition, it again becomes G. Just means it does not change, right? So any inner product of two Lorentz vectors is invariant after the Lorentz transformation. Or simply you can take it because it is repeated index. Contracted over, summed over. There's no more index, so it should be Lorentz scalar, right? Lorentz scalar by definition is invariant on the Lorentz transformation. Now, if I take the two vectors are the same thing, okay, that will mean that I take a V mu here, or it's equivalent to say I compute the log of a single vector V. Okay? I can do that, right? I can compute something like V squared, or a log of a single vector V. Eventually, I can get some number. Right? So, if someone hands you a 4-vector V, you can compute its log. If you compute its log, say for arbitrary vector, So you can have many results if you compute the long. Okay, as said, I can use this kind of notation to express what I mean. Okay, this means a norm of given vector v. If this final value as a number is positive, we call this is a time-like vector. Can you guess why this is named as time-like? Why? Can anybody notice? Why is time-like? Why is it called time-like? Yeah. Another even simple way to understand it is just take the time as a single, right? As a single component, let's say t000 something. Okay. But okay, it's not good to say in that way. Yeah, that's right. In some frame like this, you can think about some t000. Okay? Then you compute that kind of vector, you find it immediately positive. So it's time-like. Now, oppositely, if you get something negative, this is called space-like. And you can even get this is equal to 0, this is equal to lifelike. The point is, all these properties should be preserved by definition, okay? Should be preserved under Lorentz transformation. In other words, Lorentz transformation is impossible for Lorentz transformation to change this kind of property of the vector. Okay? Some time-like vector should always time-like. Space-like vector should always space-like. Definition, right? By this definition, right? This inner product definition already claimed Lorentz invariant. This property is defined from the inner product. Okay? With this solve, so makes sense. Okay. Yeah, we only have like 15 minutes. Let's quickly sketch the remaining material. Okay, so this part is about the special relativity part. Any question for this part? Okay, now let's move to the quantum part. Okay, we said that QFT is about to combine quantum mechanics with special relativity. We temporarily finished the special relativity. Now we move to quantum mechanics. Okay. So quantum mechanics, as I said, is important to understand the quantum field theory. Actually, a lot of confusion when you try to understand the QFT or when you learn QFT course. In general, people say, okay, this is too hard for some. This is too difficult in some sense. Including both calculation or technical things or conceptually, okay? But actually, one good way to overcome those difficulties, you always go back to quantum mechanics. Mostly, you don't understand something in quantum field theory just because you don't understand the same object in quantum mechanics, okay? So, in that sense, it's worth to remind you something about quantum mechanics. So, the one thing we try to remind you is the simplest harmonic oscillator. So, let's go back to our previous example, which is a point mass. A point mass is somehow stacked or attached with the spring, right? This is our favorite model, okay? It's a very simple model, right? Notice my point mass has a mass m attached with the spring, okay? 一个点怎样的东西，那位地点接上一个弹簧 ，OK？ The spring. So you can immediately write down the equation of motion, everything about this system, right? For the point of mass. Okay? The point of mass equals to 0. So according to Hooke, the equation of motion of this object should be simply go in this way. Right? Everybody is familiar with that? The first term is just force, right? It's just this is F equals to minus kx, right? Is that clear? Now, even though this is super simple, but let's try to solve this problem. Okay. So this is a ordinary differential equation. Simplify the notation a little bit. I can have dx squared dt squared plus omega squared x equals to 0. Well, I made the notation a little bit simple. Omega equals to square root k over m. Okay? Sometimes for the omega is for frequency, whatever. Okay? It's omega. I just rewrite the equation. Right? Now I want to solve this equation. Does anyone know the solution for this equation? What is the solution for this equation? Can you guess? What? That's right. So the typical solution you can guess is, of course, is the cosine sine function, right? The cosine sine function is immediately realized and solidify this property. You take the derivative twice, you get some minus coefficient come to itself, and like that. That's the property of cosine sine function. So the general solution is, of course, you can easily write down is the most general solution is the linear combination of a cosine function plus a sine function. Okay? This is solution. This is general solution. Now, I want to write it in a different way, as you already know, because I guess most of you learned the course for the mathematical physics, or mathematical method for physics, things like that. So you should know this one. But I can also write it in another way, represent it in another way, in some coefficient times a exponential minus I omega t plus another one, the A star exponential I omega t. Are you okay with this? Another form? The same thing, right? Good. Now there's a coefficient I just want to escape for this moment. Okay, let me write it down. This is actually a normalization factor. Doesn't matter, okay? It's a constant. It's a constant. The overall constant, okay? Doesn't matter. Because this equation does not depend on the overall constant. The overall constant is, again, like a solution. For sure. Now, why there is an A star here? And it will tell me. Star means the complex conjugate. Can anyone tell me why some A star appeared here? Sorry? That's right. Very good. Perfect. You should immediately realize that I didn't put something else for the A and A star. Essentially means the entire thing is real. See? You take the complex conjugate, it goes to itself. So this is A star. Now then let me try to test a little bit about your knowledge of quantum mechanics. Yeah. So now I have I have the solution, okay? If this is a homework for your classical mechanics, then it's done already. If this is the solution, you find it, that's it. Game over. Now, it's not enough to understand the quantum property of this system, right? Harmonic oscillators. So the key question now, how to quantize it? How to quantize it? Any idea? Any idea how to quantize the system? Very good. That's one way, right? That's you should, most of you should answer in this way, right? Because that's what you learned in your first course in quantum mechanics. Try to write down the Schrödinger equation, right? Is that right? Try to write down your Schrödinger equation. Solve your Schrödinger equation. You find your wave function, okay? Make all other observables in terms of operators. Just try to measure, take the average. By using these wave functions, then you can get some value of any physical observable or Hermitian operator. Is that right? That's one way, right? That's the usual way to solve this system or quantize it. But there is also another way, easier or to deal with such kind of simple system. Can anyone guess what is the better way or easier way to do it? The way we just stated is the Schrödinger picture, okay? Independently, there's also another one called the Heisenberg picture. So in Heisenberg picture, what is the difference between Heisenberg picture and the Schrödinger picture? Anyone see something? Can you say something?
Schrödinger equation sets the Hamiltonian or the operator to be the Heisenberg operator sets the wave function to be stated and the operators to change by time.
Very good. The key difference between Schrödinger picture and the Heisenberg picture is, in Heisenberg picture, the operator has time dependence, okay? Or the time evolution is characterized by the operator itself. But in Schrödinger picture, the time dependence is encoded in the wave function, or in other words, in the state. Okay, there are two different pictures, but they will be just equivalent. Okay. Now we will try to take here. Picture here is the Heisenberg picture. It's not the usual Schrödinger picture, but it doesn't matter. It's really the same thing. Okay. It's really the same thing. So let's be a little bit naive and try to quantize it in the Heisenberg picture language, okay, or framework. Now, we all know in order to quantize some classical system, such kind of classical variable x has to be promoted to quantum, okay? Which essentially means the x will become some operators, which is something like x hat, right? That should be very clear, right? That's nothing to do with different picture. It always happens, right? Right? Now, indeed, this is one way to quantize it, okay? Even though it looks a little bit naive, but that's perfectly okay. Now, let me just try to promote all the classical variables into quantum. Let's just put a hat everywhere, okay? Okay? Because this equation is so simple. I put a hat here, then I get a perfect, good, well-defined equation for the operators. You see it? Because all other are parameters, you see, including time, omega, are just parameters. This equation is so simple. It's done, right? Now, in a sense, I promoted x to x hat. I'm done, in a sense. Okay? Because in Heisenberg picture, operators are allowed to have time dependence. Now this equation basically provides you to say that if you have some operator corresponding to x, then this equation characterizes the time evolution of that operator. That's it. I get it. You see? I don't need to do anything. I just promote it. Now, in the same point, take the same point of view, I can also go to this one. Because the equation is the equation. The equation doesn't change, okay? It's just a different understanding or interpretation. Equation does not change, so the solution shouldn't change. See? This is again the solution. Okay? Now you look at the right hand side as a solution, as an operator solution. You realize something very interesting. Again, apart from A and A star, all others are parameters. You see? There's no way to assign any meaning for other parts as operators. The only possibility to interpret it as operators for this solution is A and A star. You see? Which essentially means that I should put a hat here, I get an A hat, and here I also get an A hat star. But as you know, in quantum mechanics, when we talk about the conjugate, it's better to make it into another notion. What is that? Is a dagger. That's right. Yeah, this is just the quantum mechanics correspondence for the conjugate. The dagger. Because we promoted something to the quantum level, right? You have to do some simultaneous promotion for this conjugate. Now I said that basically the job to quantize this actual variable is basically done. Indeed, it's done. Okay. You don't need to do anything else. Just think about the Heisenberg picture in the quantum mechanics. This is what you need. Okay. Now, in order to get the full message, solve everything else, including something else, not only x. This is a variable like a p. Or some other arbitrary general physical observables, you need to do something more, right? Of course. Because nobody forbids you to ask some other questions rather than this x operator, right? For instance, you can also work out the p momentum operator. So how to work out the momentum operator? I already get the x hat t, of course. The simplest way to work out the p hat t will be nothing but to work out the m time derivative of x hat t. Okay? Just work it out. You already have x hat. Now, the next step, in order to solve everything else, we should impose the commutation relation, maybe familiar to some of you. Now, as usual, we have to impose additionally quantization condition, okay, which is about to figure out the commutation of these two operators. Now these are two operators. There's a way you can define their commutator. Okay. In this case, in Heisenberg picture in particular, the quantization condition means the commutator at equal time. Okay. Just fixed time. At equal time, find your x and p. Just impose or this commutation relation. This is called a quantization condition. Right? Called a quantization condition. Now, for harmonic oscillators, this is an even simpler way to impose the equivalent condition for such kind of quantization condition. As you can check, just to plug in this solution for x hat. You also have the solution for p hat, right? Now work out this commutation relation. You immediately realize that this is nothing but a hat commute with a hat dagger equals to 1. Okay. This is the maybe some of you are familiar with. This is the so-called ladder operator trick to solve harmonic oscillator. Okay. It comes out in a very natural way if you understand this system, the system in Heisenberg picture. Now, of course, when you get a hat and a hat dagger, you just try to first define your vacuum. As usual, the vacuum is defined by this A hat. It's cleared by all the A hat. Okay, it's cleared by A hat. Let's take should be took as the definition of the vacuum state. Now, after you have this, you can try to add A hat dagger into your vacuum. Yeah, you can actually add many times. Okay. Then you can get some high excited state. For example, you can get some high excited state by acting n times. Take care of the normalization. We write it this way. So now you basically get all the state in an algebraic way in your Hilbert space. Okay.